Hi kids, we'll be going with this paper discussion. You can look into the first question. The first question says there are 5 balls. Okay, we'll be looking into the solution and I'll be reading the question. They said there are sets like pair 1 and 2. These two will be attracting, 2, 4 will be attracting, 4, 1 will be attracting, and they said 2 and 3 will be repelling and 4 and 5 will be repelling. So from here you can understand these two will be of similar kind, these two will be of similar kind. So suppose let me say 2 is positive charge, then 3 also will be positive charge, and you can see like 2 and 4 are attracting. So 4 will be negative, 4 will be negative, then 5 will be negative, right? But what is happening? 1 is getting attracted to 2 as well as to 4. If 2 is positive charge, then 4 will be negative charge, but 1 is getting attracted to both, so the meaning is it must be neutral. It must be neutral. And yeah, only that much information we can say. We can't say like it is made of metal, because like there are various examples where you can see like maybe if water is flowing and if you bring some charged rod, then the water will be like repelling because of polarization, whatever. Going to the next question, 2 fixed charges are there. So it goes like this: 2 fixed charges, 4q positive and q negative, are located at A and B. AB is 3 meters. The point P where the resultant field due to both is 0 is on which side? So if I talk about this point, this guy, field due to this guy will be in this direction, field due to this guy will be in the same direction, so it can't become 0. Now if I talk about this point, field due to this guy will be in this direction, field due to this guy will be in this direction, but this distance is closer to the bigger charge, right? So this field will be more, it can't be cancelled because of that guy. So here, though the forces are in the fields are in the opposite direction, it won't become 0, but here it can become 0. Now if I look at immediately after minus q, there will be like the field will be in this direction. So if I take one unit positive charge and if I keep it here, then it will be attracting because this force will be very large. But when I keep moving it, what will happen? The field because of this guy will be reducing. The field because of this guy also will be reducing, but this guy due to this guy it will be reducing in a slower rate. You can see like when you go to infinity, when you go very far away, you will be feeling this center charge is 3q. This center charge is 3q. So right now the field is 0. At some point the field is going to become 0, that is the field because of this guy will be cancelled by field because of this guy. Now what will happen if it is a positive charge, if I put it this side, what will happen? Now field because of this guy is more and due to this guy is less, so it will be attracted this way, so it won't be stable equilibrium. But if it is a negative charge and if I put it here, what will happen? Field because of this guy is more, so it will be repelled. Field because of this guy is less, so it will be attracted. So repulsion is more, so it will be going in this direction. Now similarly, if I talk about here, if I put it here, what will happen? If I put a negative charge here, then field because of this guy will be more, due to this guy will be less, so it will be attracted back. So this is going to be stable equilibrium for negative charge, right? Okay, there are some statements in the next question. A charged particle always moves along electric line of force. So it need not be, I'll show you that later. A charged particle may move along line of force. So let me go with this option. If the electric field lines are this way and if I keep positive charge here, what will happen? That positive charge will, on that positive charge there will be force in this direction, so it will be accelerating in this direction. So it will be going along the line of along the electric field line. That can happen, it may happen. Option C, a particle never moves along line of force, but here it is moving along line of force, so it can move along line of force. So from here I can say B is correct and C will be wrong. Now going for A and D, now look at this thing. If I put positive charge here, what will happen? Because so electric field is in this direction, so velocity will be increased in this direction, so it will try to move in this direction. Now once it moves slightly in this direction, what will happen? The field is in this direction, so the force will be in this direction. Now there is angle between velocity and acceleration. So when there is angle between velocity and acceleration, you can see like there will be velocity component along acceleration, or yeah, okay, fine. So there will be velocity component along this direction and perpendicular also, right? So along apart from the motion in this direction, there will be motion in this direction also. So it won't be going along the line. There will be some motion in the perpendicular direction also. So it won't be going along the curved line. If it is a straight line, like previous case, it would have gone. But if it is a curved, it won't be going along the curved line. It will be going in some random direction, right? So option D, a particle moves along line of force if it is released from rest. No, need not be. A particle always moves along line of force? No, need not be. Okay, going to the next question. A thin walled spherical conducting shell of radius r is given a charge q. The same amount of charge is placed at center. So now I will be taking Gaussian surface. Electric field in the material of the conductor will be 0. So flux is going to be 0. If flux is 0, total charge enclosed will be 0. There is q already, so this will be minus q. But the total charge on this guy is q, they said. So if it is minus q here, outside it will be plus 2q. Now this is at the center, so this will be uniform distribution. This will also be uniform distribution. On the outer surface, charge density will be, so total charge is 2q by surface area is 4 pi r square, 2q by 4 pi r square. So option A will be correct. Now electric field is 0 at all points inside S. So inside, field because of this guy is 0 because it is uniform distribution. Field because of this guy also will be 0 because it is uniform distribution. But field because of this guy won't be 0. So option B is wrong. At any point outside S, the electric field is double the field. Okay. At a point just outside S, the field will be double when compared to just inside. So just outside, field because of these two will be 0. Field because of this guy will be k into 2q by r square. Now if I want to talk about field here, field because of this guy will be 0, this guy will be 0, field because of this guy will be kq by r square. Kq by r square here, k2q by r square, so it is double. At any point inside us, the electric field is inversely proportional to square of distance from C. Yes, if this distance is r, field because of this guy is 0, this guy is 0, so field because of this guy will be kq by r square. It is inversely proportional to r square. Yes. Okay, the next question. An electric dipole is placed at the center of a sphere. An electric dipole is placed at the center of sphere. Mark the correct options. The flux of electric field through the sphere is 0. Flux depends on what is the total charge enclosed. Total charge enclosed is 0, so flux will be 0. The electric field is 0 at any point on the sphere, so it's not. Here it is 2 kb by r cube, here it is 2 kb by r cube, kb by r cube. So E bar need not be 0, but overall E bar dot ds bar for the closed loop, for the closed structure, that 3D structure, right? So for the closed Gaussian surface, it will be 0. Electric, okay, then electric potential is 0 everywhere. So electric potential is not 0, it is like cos theta, it is a function of cos theta, right? But if I talk about the potential here, it will be 0. So if I take this equator thing, then the potential here, everywhere will be 0. So there will be a circle where the potential is going to be 0. So that says option D is correct. A uniform surface density 8 sigma exists over the entire xy plane except for circular hole of radius. Okay. The electric field at point 0, 0, root 3a. So basically there is a sheet and you are removing disk. So you need to find the field because of sheet and field because of disk, and you need to subtract them. Field because of sheet is sigma by 2 epsilon, but here sigma is 8 sigma. Now field because of disk, when it is like this, when the angle is theta, field because of disk is going to be sigma by 2 epsilon naught into 1 minus cos theta. So you can go with that, sigma by 2 epsilon naught into 1 minus cos theta, but sigma is 8 sigma here, so you can do the subtraction. These two will be getting cancelled, you will be ending up with the answer. Two fixed equal positive charges each of magnitude something was given are located at E and B separated by distance. An equal and opposite charge moves towards them along line COD. The perpendicular bisect. Okay, the moving charge when it reaches the point C has kinetic energy. So what is the farthest distance it can reach? So basically when it is here, it has kinetic energy 4, potential energy, so potential energy between these two. I am not bothered about the potential energy between these two because it is not going to change. So potential energy between these two will be minus, this charge is negative, right? So minus kq square by this distance. Similarly between these two is the same thing, so 2 times of this. This is the potential energy and kinetic energy. So it will be attracted and it will be going here. While it is going here, again it will be attracted, so it will be reducing its speed and it will come to rest somewhere. So when it is coming to rest, kinetic energy is 0, potential energy, let me say this distance is r. So potential energy between these two will be this much. Similarly potential energy between these two will be again the same thing, so 2 times of this will be the potential energy. This total energy is converting as potential energy, right? So when you calculate this, you will be getting total energy initially is -5, so total energy finally also must be 5. From there you will be getting R is 9. Once you get R is 9, then you can use Pythagoras theorem and you can find what is this distance. Two concentric spherical shells. The inner sphere is given a charge. The electron escapes from the inner sphere with negligible speed. Assume that the region between the spheres is vacuum. The speed with which it will strike the outer surface. So there is negative charge here. Electron is having zero speed, almost zero speed here. So what will be the potential energy? Potential energy will be, this is negative charge, electron is negative charge, so potential energy is going to be positive, k q1 q2 by r, k q1 q2 by r1. This distance, this radius is r1. Now from here it is going here, so here the potential energy is going to become k q1 q2 by r2, distance is r2. Only this has charge, they never said it is conducting or something, so this doesn't play any role. So potential energy here is this much and kinetic energy half mv square, and I can go with energy conservation. Initial potential energy plus kinetic energy will be same as final potential energy plus kinetic energy. You can substitute the values, but when I am substituting the values I am not getting the given answer. See, though it's going like relative speed, like we can't do this way, still like at least theoretically we will be going this way, classical approach, right? Yeah, they have given E by M ratio, so I am converting it into E by M form so that I can substitute it. A solid sphere density is of this form. So electric field at r by 2 is 1 by 8 times of electric field at r. So by symmetry I can say if I want to find the field anywhere it will be kq by, see, if I want to find at a distance r, I need to find what is the at a distance r by 2, I need to find what is the charge inside r by 2, then I can go with k into charge by r by 2 square. Similarly, if I want to find the field at a distance r, k into charge enclosed by r square. They said this is 1 by 8 times of this, but charge enclosed here and the total will be different. So if I want to find what is the charge enclosed, what I will be doing, I will be taking an element of radius x and thickness dx. So charge on that element is going to be density into volume. Volume is surface area into thickness. This is the charge on the element. So if I integrate it, I will be getting the total charge. Now this density is given as function of r. Yeah, so I will be getting the charge. Now from 0 to r, so if I integrate from 0 to capital R by 2, I will be getting small q. If I integrate from 0 to capital R, then I will be getting capital Q. So anyway, I have integrated from 0 to small r. Now if small r equals to r by 2, capital R by 2, I will be getting this. If small r equals to capital R, I will be getting this. So I am just substituting it back here. And q equals to q by 32 you will be getting. So small q and capital Q I need to substitute. For small q, I will be putting this as r by 2 and I will be substituting. For capital Q, I will be putting this as capital R and I will be substituting. And yeah, then you will be ending up here, right? So this is 2 power 5, A equals to 2. The next question, basically they have given the charges, they have given the masses, and there is a spring and this length is 2. So right now, I mean this is fixed, this can be movable. So the force on this guy will be kq1 q2 by r square. So when you substitute the values and when you calculate, it will turn out to be 2.25. So friction, maximum friction here, when you calculate mu mg, it is turning out to be 2.5. So repulsion force is 2.25, but maximum friction is 2.5. So friction will provide 2.25. So repulsion force is 2.25, friction will be 2.25. So it will be in equilibrium only. So there won't be any extension. So answer is going to be, the distance between them is going to be 2 only, right? Thank you.